Hello everyone. Here I am explaining one method of solving a second order linear ordinary differential equations. And as we are aware of that, there are many methods of solving a second order linear ordinary differential equations. But I am stick on to one particular method of solving a second order linear differential equation. Solving means we have to find out a solution for a second order ordinary differential equation. Okay. What means second order ordinary differential equation is? Firstly, second order ordinary differential equations looks like d square y by dx square, wait, d square y by dx square plus p into dy by dx plus q of y is equal to r. This is a general representation of second order linear ordinary differential equation. Okay, what mean this PQR? PQR are functions of x or maybe constants. So the general form of a second order linear differential equation looks like this. So as I have already told, there are many methods of solving a second order linear differential equations. So where PQR are functions of x. Functions of x are maybe a constants. So what happens if PQR are constants? All PQR are constants. All are constants. If all are constants, we call this as linear differential equations having constant coefficients. If all PQR are constants, then it is said to be a second order linear differential equation of constant coefficients. For example, d square y by dx square plus 2 into dy by dx plus 3 of y is equal to some 4. This is nothing but a second order linear differential equations having a constant coefficients. So as we are aware of that, we can easily solve this method by using just by taking d by dx is equal to some d and d square by dx square as some d square, and we can find out a complementary function as well as particular integral. Therefore, if PQR are constants, then our job is simpler. This reduces to linear differential equations having a constant coefficients, and we already know there are many methods for solving a second order linear differential equations having a constant coefficients. But now I am not stick on to this type, that is PQR or all PQR are constants. At least one of PQR are variables or functions of x. Sorry, that need not be variables, any variable always, that must be a function of x. So that is at least one of PQR must be function of x, then this method holds. That is, this method generally useful only when at least one of PQR are function of x. This is nothing but if at least one of PQR are functions of x, then it is nothing but a linear differential equation having variable coefficients. So this method mainly useful only when at least one of PQR are functions of x. If all PQR are constants, then we can use this method, that is d by dx is equal to d, and replace d by m and find out the corresponding complementary function as well as particular integral. Therefore, this method, that is the name of this method is when a part of complementary function is given or reduction by its order. We can call by using both the names, that is when a part of complementary function or by reducing its order. This is the name of this method to solve a second order linear differential equation having variable coefficients. I am stick on to variable coefficient, that is at least one of PQR is a variable, or that is generally a function of x. Okay, the general form of second order equations be like that: d square y by dx square plus p into dy by dx plus q of y is equal to r. This is general form. That is, suppose if x square into d square y by dx square plus p into so on, you must divide this by divide the coefficient of d square y by dx square. Therefore, you must make coefficient of d square y by dx square is equal to 1. That is a general form of second order linear differential equation, where PQR are functions of x are constants. I am already told at least one of PQR must be a function of x. Then only this method useful. Otherwise also it's useful, but instead of this method we can use many other methods. Okay, So first, the name of this method is when a part of the complementary function is given. That is, first we must know what do you mean by complementary function. Complementary function is one which satisfies the which satisfies the corresponding homogeneous part, which satisfies the corresponding homogeneous part in a differential equation. Corresponding homogeneous part in a differential equation, which satisfies mean it is a solution of the homogeneous part in a differential equation. Here in this differential equation, in this equation 1, homogeneous part is nothing but if you just equate RHS is equal to 0, you will get the homogeneous part in this differential equation. So complementary function mean it is a solution of the homogeneous part in a given differential equation. So let y is equal to u be a known integral of the complementary function, because this method holds only when if you know the part of a complementary function. Otherwise, we have a many other methods to solve a second order linear differential equation, like variation of parameter, or by changing independent variable, or by changing dependent variable. If you know a part of a complementary function, then only you have to use this method. Okay, y is equal to u is a solution of this corresponding homogeneous part, that is d square y by dx square plus p into dy by dx plus q of y is equal to 0. It is a solution mean it must satisfy this equation. That is nothing but if you replace y is equal to u and if you differentiate twice, it must satisfy the differential equation. Therefore we will get d square u by dx square plus p into du by dx plus q of u is equal to 0. If you know the part of complementary function, this must satisfy this equation. Okay, let the complete solution is in the form of y is equal to u into v. U is already you know, that is a part of a complementary function. You must find out v, where v is nothing but a function of x. So you have to find out the value of v. V is generally a function of x. That is not a value, that is a function of x. Therefore, we have to determine the v. Complete solution is in the form of y is equal to uv. That is, it is simply like we have changed y is a dependent variable. We have changed it to other two variables, y is equal to u into v. Therefore, you must change dy by dx to either du by dx or dv by dx. Because y is a dependent variable, we have changed the dependent variable into whatever some variables. Therefore, you must simplify d square dy by dx in terms of du by dx or dv by dx. Okay, just a minute. Okay, after substituting the solution is in the form of y is equal to u into v, you have to differentiate this with respect to x twice, that is with first with respect to x, again whatever the solution we will get, again differentiate that with respect to x. Therefore, this is y is equal to u into v, differentiate this with respect to x. We have to apply product rule, that is dy by dx is nothing but u into dv by dx plus v into du by dx. Again differentiate this with respect to x. We will get d square y by dx square as, okay, first you must remember this equation. This is very very important. Equation 2. Okay, y is equal to uv. Differentiate this with respect to x. For one time differentiate, you will get this term. Again differentiate this with respect to x. You will get first term in differentiation of this d square v by dx square. Again you will get du by dx into dv by dx. Here also you will get dv by dx into du by dx. Therefore, since derivative exists, they are continuous. Therefore, du by dx into dv by dx is same as dv by dx into du by dx. Therefore, here 1 du by dx into dv by dx. Here also you will get 1 du by dx into dv by dx. Therefore, 2 times du by dx into dv by dx plus here v into d square v by dx square. Just differentiate this and just simplification, you will get this term. This is d square v by dx square. Therefore, now we will have y is u into v, and we also have dy by dx, and we also have d square y by dx square. Therefore, just you have to simplify or you have to substitute these expressions these equations in the given equation. This is a given equation. You have to substitute for d square by dx square, dy by dx as well as y. You will get corresponding equations, and those equations are, that is d square y by dx square plus p into dy by dx plus q of y is equal to r. So d square y by dx square is nothing but this expression. So first I write this expression because for simplification it will be very helpful for me. Therefore first I have write this expression, that is v into d square u by dx square plus 2 into this plus u into d square y by d square. This is a d square y by dx square part. This is d square y by dx square part plus p into dy by dx, and this is dy by dx part. See here, dy by dx is nothing but u into dv by dx plus v into du by dx. Therefore I have retained the same. Again, okay, plus q, here just see, plus q into y, y is nothing but u into v is equal to RHS is same, that is r. Okay, again simplify, collecting the coefficients of v. Here there is a v term, its coefficient is d square u by dx square, and here there is a v term, their coefficient is, we have to multiply this p into du by dx, therefore p into du by dx, plus here also there is a v term, therefore v, here I take it as a common, q into u, plus here I am collecting the coefficients of u. Here there is a u term, you will get d square v by dx square, and here also there is a u term, you will get p. Remember this one, you must multiply this p, and after this you can take the coefficients of u as well as v. You must remember this, very very important in the next steps, in future steps. Okay, fine. U into d square v by dx square plus p into dv by dx plus 2 times of du by dx into dv by dx is equal to RHS is same, that is r. Therefore we must already know that u is a part of a complementary function, therefore it must satisfy the corresponding homogeneous part. That is, homogeneous part is d square by dx square plus p into dy by du by dx plus q into u. This is equal to 0. We have already simplified that. This d square u by dx square plus p into du by dx plus q of u is equal to 0. Therefore substitute for this expression as 0. You will get, okay, v into 0, which is nothing but v into 0, you will get 0. Therefore you will left out with this term. You will get u into d square v by dx square plus p into dv by dx plus 2 into du by dx into dv by dx is equal to r. Again just I have some simplification to one nice form, so that just divide this term by u. You will get d square u by dx square, these are all one single term, plus p. Okay, just I want to write another step, that is here after dividing this by u, you will get d square v by dx square plus p into dv by dx, these are single term itself, plus 2 by u into du by dx into dv by dx is equal to r by u. Divide whole equation by u. Therefore now d square v by dx square, this is the first term, d square v by dx square. Again I am just collecting the coefficients of dv by dx. Here also dv by dx, here also dv by dx. Therefore dv by dx into p plus 2 by u. P plus 2 by u into du by du. You will simplify, you will get the same expressions itself. Okay, p plus 2 by u into du by dx is equal to r by u. Therefore now we have to solving for a v. Therefore again this is again we didn't know how to solve this expression. This is again a second order differential equation. Therefore we have to reduce this order to some other orders, again solve for a v. Therefore Now put dv by dx is equal to some q. Put dv by dx is equal to q, because in this term also we didn't know how to solve these expressions. Therefore we have reducing of second order to a first order, because if it is equation in the form of dy by dx, okay, in the place of y it is dv by dx plus, or a general form of a first order linear differential equation, dy by dx plus p of y is equal to q. Suppose the equation in the form of this expression, then we know this method of solving this equation, that is the linear differential equation. Therefore we have reducing the second order to a first order. It will reduce us to the known methods, that is it may be variable separable form, or it may be a linear differential equation of order 1. Therefore, we are substituting in place of dv by dx as a q. Again differentiate this. Differentiate this, d square y by d square y by dx square is not q square, because differentiating. Therefore, d square v by dx square you will get correspondingly dq by dx. Substituting this in this equation 6, we will get d square v by dx square is nothing but dq by dx plus p plus 2 by u into du by dx into dv by dx as q. We have taken it as a q is equal to r by u. Therefore here in from the first expressions, the differential equation is second order by, but after substituting this expression dv by dx is equal to q, this reduces to order 1. See here, p is a function of x, u is a function of x. If it u is a function of x, differentiate this, you will get the same function of x into q is equal to r by u. Therefore second order differential equation reduces to first order. Therefore the name reduction of order. There are two names, or we call by two names, that is when a part of a complementary function is given. This we already know, where this is a part of a complementary function, or reduction its order. That is, we have reducing the second order differential equation to a first order and solve the corresponding value of v. Therefore the name reduction of its order. Now we have reduced the second order differential equation to a first order, that is dq by dx in place. Okay, if it is like this, we have a methods to solve it, that is by finding integrating factor we have to find a solution of this differential equation. In terms of y, here it is a q, that is dq, that is here it is a small q. Must remember this is a small q, dq by dx plus, these are all the terms, these are all the function of x, like p itself, because p is a function of x, u is again a function of x, this is also function of x, this r is again a function of x. We have already taken p, q are functions of x, u is a function of x, therefore r by is also function of x. Therefore this is a linear differential equation in a dependent variable q and a independent variable x. Therefore solution is in the form of not y into integrating factor is equal to integration of q into integrating factor dx plus c. In place of y we will have q. Therefore q into integrating factor is equal to integration of whatever the RHS, you take it as a q into integrating factor plus c. So that is the solution of this differential equation. Therefore which is linear in q and x. The original equation is now reduced its order by 1. Original equation is d square by dx square plus p, that is a general form of second order linear differential equation, that is reduces to this expression or this equation. Therefore it is reduced by 1. Therefore we call it as a reduction by its order. Therefore solution for this, okay, first we have to find out the integrating factor. After this you will know by in problems you will know easily how to solve these differential equations. Sometimes it reduces to variable separable form and sometimes it is linear differential equation, but since here I am explaining generally, that is we call simply as a derivation. Therefore in generally I have explained, that is integration factor or integrating factor, that is if is nothing but integrating factor of this expression is nothing but e power integration of this term. This term is p plus 2 by u into du by dx. This is du by dx with respect to x, which is nothing but e power integration of Okay, split the integration to both the terms. We will get p into dx. Here dx get cancels. You will have integral 2 into 1 by u into du integration is log u. Again you will have 2. Therefore p dx plus 2 into log u, which is nothing but e power, okay, I'm just splitting e power m into n is nothing but okay, e power m plus n is nothing but e power m into e power n. Therefore e power m plus n is nothing but e power m into e power n. Again we know by one identity using logarithm, e power log x to base e. Here the base must be is equal to e is nothing but x. Whatever the term here, we will get the same. By reverse taking log, you will get the same expressions, or you can just verify those expressions. Okay, just remember e power log whatever the base term to base e, this must be is equal to e is equal to this term itself. Therefore e power log u square into log base, this is nothing but u square, this is the base e into this is into e power integration of p dx. Therefore this is the integrating factor. This is generally term, this is a general term in integrating factor. Therefore solution is nothing but y into integrating factor in case of dy by dx, but here it is case of dq by dx. Therefore q into integrating factor is this. This is integrating factor, this is integrating factor. Integrating factor is equal to integration of q. Q is nothing but whatever it is in the RHS. Don't confuse with the first q, that is a general differential equation q, with this term. If it is confusing, call this as some p1, call this as some q1. q1 is nothing but r by u into integrating factor with respect to x plus integrating constant, call it as c1, because after finding a solution of a second order differential equation, you will get two constants. Therefore one constant call it as c1, another constant call it as c2. Therefore q is nothing but we have substituting dv by dx in place of q. We have taken dv by dx as a q. Therefore replace the same in place of q. You will get q is nothing but dv by dx, which is nothing but okay, just divide by this integrating factor. You will get divide for both the terms. You will get e power okay, e power divide, okay, e power 1 by e power x is nothing but e power minus x. Therefore we have taken this to numerator. You will get e power minus integration of p dx divided by u square into this term is same, u will get cancels, ru into e power integration of p dx plus c1 by u square, this c1 by u square, divide this by, okay, divide by integrating factor, this divide by integrating factor, you will get c1 by u square into e power integration of minus p dx. For on integrating, these are all, since I am generally defining, you will get a big terms of integrating factors as well as a solution for v, but in case of a problems you will get simplified, you will get a simplified form, just like one or two terms. But since it is a general term or a general derivation of a second order linear differential equation, therefore we will get these type of complicated expressions. Don't worry about it. When you go to when we go to problems, it will be bit very simplified form. Okay, fine. Q is nothing but dv by dx. On integrating we get v is nothing but, on integrating mean you have to integrate with both LHS as well as RHS. In LHS we will get integration of dv, which is nothing but v. In RHS we will get all this term with respect to x, all this term with respect to x. Therefore integration of this whole term 1 by u square into this with respect to x. I'm just splitting directly, I'm splitting those two expressions because you have to integrate both two expressions. Just I have to split the integration for both the terms. You will get integration of this with respect to x as well as integration of this with respect to x. It is 1 by u square into this. Therefore putting the value of v, okay, this is nothing but the required value of v. Clearly see here, see this is okay, this is on integration, this is a c1 constant from we get from this expression. On integration we will get another constant, because we have integrating two times. If we integrating first time we will get one constant, if we integration with another time we will get another constant. Therefore here we will get C1. On integration we will get another constant, call it as C2. This is C2, integration in this expression plus C2. Therefore, which is nothing but the value of v. Clearly u is a function of x, this is a function of x, these are all functions of x. With respect to x integration we will get the in terms of x itself, here also in terms of x. Therefore this is a required value of v. What we want to find out the value of v, here we have obtained the value of v in terms of x. Clearly v is a function of x. Therefore putting this value of v, because complete solution is in the form of y is equal to uv. Again u is a function of x, v is also function of x. We have to determine, here we have determined the value of v, function of v, sorry, v is a function of x. We have determined the v. Therefore complete you have to write is in the form of y is equal to uv, because we have already told the complete solution in the form of y is equal to uv. So y is equal to u into v. U is nothing but when a part of CF, this is a part of CF. Therefore u into v, you have to multiply for this term by u. Just you have to multiply this term by u. You will get, here there is a single term C2. Therefore C2 into u plus this term into u, this whole term into u, you will get, okay, I have written first this term. This is C2 into u, this is C2 into u, this is C1 into, okay, here we have different integrating this with respect to x. Therefore u square is constant, and we have multiplied by u. One u get cancels. Okay, sorry, the expression is same. This is multiplication, this expression is we taken it as the same. 1 by u square into e power minus integration of p dx plus u into, okay, 1 by u square, this is 1 by u square, multiplying this by u into this term. Okay, this is a complete solution for a second order differential equation, mainly for a variable coefficients, and that too if you know a part of a CF. That is, clearly this has a two arbitrary constants. Two arbitrary constants, one is C1, another is C2, because for a second order linear differential equation, if you say anything is a solution of this differential equation, that must contain a two arbitrary constants, then only it is a solution for a second order linear differential equation. Therefore in this step we have clearly said that this is a solution for a second order linear differential equation, because it has two arbitrary constants, which includes the, okay, this is nothing but the same, which includes the solution y is equal to u, that is a part of CF. Hence this is a required complete solution, because complete solution is in the form of y is equal to u into v. Clearly if this is a solution, this must contain two arbitrary constants, C1 as well as C2. Therefore this contains two arbitrary constants, C1 as well as C2. Therefore this is a solution for a second order linear differential equation if you know a part of a complementary function. Okay, just revising this, you must remember, okay, 3 to 4 expressions. If you solve a second order linear differential equation, whenever you know a part of a CF, you must remember 3 to 4 steps. That is, first you have to convert to a standard form. Okay, convert to standard form, and again find out the value of u. That is, you must know, or in the question itself they have given this is a part of a complementary function. Therefore, okay, you must know a part of CF. Again remember this expression, that is d square v by dx square, this expression you must remember this expression. Later you have to substitute, because you have to reduce this to order 1, du by dx is equal to q. After this you will get it follows because it reduces to linear differential equation as well as variable separable form. This must easily follows. After these steps you will know, you must remember just solution is the form of y is equal to u into v, as well as you must know, you must find out the part of a CF. Okay, Ram tried to explain generally to find out a second order linear solution for a second order linear differential equation with the method of when a part of a complementary function is given. If you have any queries or any doubts, you can text in a chat box. In later stages, I will add a few more methods to solve a solution for a second order differential equation, or I have to solve some problems on this method, and later I move on to another. There are 2-3 methods to solve a second order linear differential equation. There are mainly we are using 3 to 4 methods to solve a second order linear differential equation. Mainly we have used variation of parameters that I will make in another videos. Okay, thank you for watching.